Hi, my name is Leo. Today we are going to talk about electrostatics. Electrostatics is a branch of physics which observes stationary or slow-moving electric charges. It observes static electricity, which is an imbalance of electric charges within or on the surface of a material. Electricity means the presence or flow of electric charges. There is also the type of electricity other than static electricity, called current electricity, which is flowing rather than static charge. Electric charge, marked with BQ, is a physical property of matter, which causes it to experience a force when put in an electromagnetic field produced by electrically charged object. Its measuring unit is C, Coulomb, unit derived from the basic measuring units for electric current A, ampere, and time S, second, so it is C, Coulomb, equal to ampere second, AS. All electric charge is quantized, meaning it consists of the elementary electric charges, which are the smallest units of energy. Therefore, every electric charge is a multiple of the elementary charge, which is charge of proton or electron, and is marked with small e, and it's approximately 1.6 times 10 to the minus 19th power coulombs, where proton is positive electric charge, so it has a charge of plus e, and electron is negative, so it has charge of minus e. How to calculate electric charge of a charged object if we know the number of protons and electrons in it? We have to calculate the difference between these two numbers so as to get how many protons are there more or less than the number of electrons, and then multiply the gotten value by the elementary charge E, since we know total charge of an object has to be multiple of E. So we have this formula that Q, charge of an object, is number of protons minus number of electrons times elementary charge E. When electric charge is calculated, we can conclude if an object is positively, negatively charged, or electrically neutral. If the number of protons is greater than number of electrons, it means the object has lost a number of electrons, while the number of protons remains same. In this case, the object's electric charge is positive. If the number of protons is smaller than number of electrons, it means the object has gained the number of electrons while the number of protons remains same. In this case, the object's electric charge is negative. Finally, if the number of protons is equal to number of electrons, it means the object has neither lost nor gained the number of electrons while the number of protons remains same. In this case, the object's electric charge is zero. We say it's electrically neutral. However, it's important to say, even if an object is electrically neutral, this has nothing to do with distribution of electric charges. An object can have non-uniformly distributed electric charges, for example to be polarized, and then it's called electric dipole. This can happen because, for example, molecules which become polarized, so they become energetically more stable, which is primarily related to electronegativity property of chemical elements. We can polarize a balloon with a piece of cloth by rubbing it onto its surface, and then balloon's charge separates into two main groups, positive charges on one side of balloon and negative on the other. The same is with cloth, as we can see. Charge density is a measure of electric charge per unit volume of space, which can be measured in one of three dimensions depending on the object where the charge is distributed in. The first type is electric charge density per unit of length. It's appropriate for charge density of, for example, a stick, whose other two dimensions are negligible compared to its length dimension x. It's calculated using this formula, where delta Q is an amount of electric charge and delta x is a unit of object's length, where the delta Q charge is situated. It's measured in coulombs per meter. The second type is charge density per unit of surface area. It's appropriate for charge density of, for example, a table whose other dimension is negligible compared to its length and width dimension. It's calculated using this formula, that sigma is delta Q over delta S, where delta Q is an amount of electric charge and delta S is a unit of object surface where the delta Q charge is situated. It's measured in coulombs per meter squared. The last type is charge density per unit of volume. It's appropriate for charge density of, for example, a cube, where all of these three dimensions are important. This type of charge density is calculated using the next formula, that rho is delta Q over delta V, where delta Q is again an amount of electric charge and delta V is a unit of object's volume where the delta Q charge is situated. It's measured in coulombs per meter cubed. We can measure how much an object is charged using an instrument called electroscope. Here we have an electroscope. It consists of conductor, such as copper wire, fixed in a vessel or bottle, and two aluminum leaves hanging on the hook of conductor. Furthermore, we bend the conductor in form of a spiral at the top so as to make it detect charge more efficiently. It functions in the next way. If we take, for example, a uniformly negatively charged object, it attracts positive charge protons on the top of conductor, and consequently, negative charges, electrons, are repelled to the bottom of conductor, which causes aluminum foil leaves to become charged with the negative charge, and as a result they repel from each other. The more charge an object has, the leaves repel more, that is, the angle enclosed by them is increased. Now I'll show you an example of electroscope detecting charge with charged plastic stick and cloth. When rubbing the plastic stick against the synthetic cloth, the stick will become negatively, while the cloth positively charged. We'll bring the stick close to the electroscope. So what we can expect? We can say negative charge of the conductor wire is going to be repelled from negative charge of the stick, which is why aluminum leaves are going to repel from each other. Let's do that. Once more for you to see closer. Coulombs law is the law which enables us to calculate electrostatic force, also called Coulomb's force, which is force which acts between two electric charges, knowing position of the charges in space, which also includes distance between them and their electric charge. These charges are so-called point charges, which are charges whose dimensions, whose radii, are negligible compared to distance r between them. Let's take an example of two charges Q1 and Q2 you can see here, which have opposite sign, so one is negative and the other is positive. And distance between them is little r. We can say they would attract each other by the force of same magnitude but opposite sign. The force we are talking about is electrostatic, it is Coulomb's force, which is mathematically expressed using the next formula. So Fe, meaning electrostatic force, is K times Q1 times Q2 over R squared, where F is electrostatic, it has Coulomb's force, Q1 and Q2 are these two charges, R is distance between the charges, and K is constant of proportionality, which primarily depends on the medium where charges are situated within. It's usually taken that it is K for vacuum medium, which is 9 times 10 to the 9th power Newton meter squared per Coulomb squared. K is actually calculated as 1 over 4 pi epsilon r epsilon 0, where epsilon 0 is constant called vacuum permittivity or permittivity of free space or electric constant, and where epsilon r is constant called relative permittivity or dielectric constant. It is permittivity expressed relative to vacuum permittivity and is not always included in Coulombs law expression. The equation which connects these two epsilons, permittivities, is epsilon equal to epsilon r times epsilon 0, so it's absolute permittivity or only permittivity, which is product of these two permittivities. What's useful to say is also that Q1 and Q2 charges are often expressed as small q and big Q, where small q is called test charge and big Q source charge. Test charge is test particle, which is an idealized model of a particle, whose certain physical properties are chosen to be relevant while others are considered negligible, since they don't play a significant role in the observed situation. In the case of test charge, it is its electric charge which is important property considered. By using all of these constants and expressions, we can express complete formula for Coulomb's law, so that electrostatic force Fe is K, which is equal to 1 over 4 pi epsilon r epsilon 0, which is actually their product is absolute permittivity, times Q test charge times source charge big Q over r squared, which is distance between them. Electric field marked with big E is a part of space where acting of Coulomb's force on an object is significant. It's a physical quantity used to quantitatively express electric field, which is defined anywhere except the very place where point charge is situated, where it diverges to infinity. Electric field is a vector which does move together with a moving charged particle. If a point charge does not move, meaning it's stationary, then its electric field is also called electrostatic field. To measure electric field, we have to know amount of electrostatic Coulomb's force and charge of this test particle, which is usually placed at position where no charges are present. So we have this formula that electric field is proportion of electrostatic force Fe over Q, which we can also express for electrostatic force F equal to Eq, as we can see here. And you can see that its measuring unit of electric field is Newton per Coulomb. How can we visually represent electric field? For that we have field lines, lines which are imaginary, not real, but here they are for us to describe electric field as a vector, since it is a vector quantity. Any arbitrarily chosen point of space has its vector of electric field E, and it is always a tangent on field line at the chosen point. Here is chosen point P, as you can see. It's important to say it's impossible for one point of space to have more vectors of electric field, which would mean that electric field has more directions, which is impossible for it to have as a vector which has to have one and only one direction. Let's draw this scheme of electric field example. Positive charge is usually taken as source, and meaning start of field lines, and negative charge is its sink, end of field lines. Electric field does not go through an object, so we draw it in the way that electric field lines only go from positive to negative charge, from its source to its sink, and this direction is indicated by arrows. Electric field of a point charge can be calculated using the next form of Coulomb's law we've got using expression for electrostatic force and electric field. So it is electrostatic force over Q. If we put expression for electrostatic force, we got this, And from this we get the final formula that E is equal to K times source charge Q over R squared. You can see this formula is very similar to Coulombs law formula, although here test charge small q has disappeared because it was cancelled out of equation when dividing F by small q. The special case of an electric field is a homogeneous electric field. And it is an electric field equal at all of its parts, meaning all electrostatic force vectors on test charge in the field are equal. That is, they have the same magnitude and direction. Therefore, field lines of this electric field are parallel to each other and equally dense, meaning apart from each other at the same distance. That kind of electric field is present in capacitors. For example, we are going to talk more about in the next video about electrostatics. Electric flux C is a measure of law of electric field through a given surface area at a given angle from surface vector. It is calculated using this formula, where C is equal to E times S's vector, or E times S times cosine theta, where theta is the mentioned angle between surface vector and electric field vector. The second expression is actually scalar product of vectors E and S. And from this we get that its measuring unit is Newton meter squared per coulomb. Surface vector is a vector which is perpendicular to an object surface and has one of two possible orientations. It's positive when it goes out of the body's volume and negative when it goes into it. Let's take an example of an object where surface vector goes out of the object's volume, which means it has positive sign. Furthermore, electric field is in the plane of the screen and goes rightwards. From the formula we can calculate electric flux in the next two special cases. So the first special case is when surface vector is parallel to electric field vectors. And then the angle theta between them is 0. So cosine 0 is 1. And then psi is equal to E times S. So electric flux is in this case the biggest possible, so it is psi max. The second case, where surface vector is normal vector to electric field vectors, it's perpendicular to them, which means that angle theta is 90 degrees. So theta is 90. And then cosine of 90 is equal to 0. Therefore, psi, this electric flux here, is equal to 0, so there is no electric flux in this case. Is the case when it's the smallest possible. It's psi minimum. In this video you've learned the basics of electrostatics. Thanks for watching and stay with us.